Okay, so picture this. You've got a system that needs to spit out over 1 million unique IDs every single second. At that kind of scale, the usual tricks, they don't just bend, they completely break. They can actually take your whole system down with them. So today, we're rolling up our sleeves. We're not just going to talk theory, we're going to architect a real, production-ready solution for generating IDs at an absolutely massive scale. Let's dive in.
So what does massive actually mean? Well, let's put a number on it. We are talking about 100 billion requests every day. That breaks down to about 1.15 million requests per second. Think about that for a second. At that speed, your standard playbook, just using a database auto-increment or a basic UUID, it just completely falls apart. It's not even in the same league. It's a totally different class of problem.
All right, so here's how we're going to tackle this. First, we'll lay out the ground rules, the big challenges of ID generation at this scale. Then we'll look at why legacy, centralized systems just don't cut it. After that, we'll dive into UUIDs, the uncoordinated approach. That'll lead us to the snowflake paradigm, which is really the star of the show. And finally, we'll get practical, building a production system, and even touching on some advanced topics like hotspots and using services like Spanner.
Okay, let's kick things off with the foundation. Before we can even start talking about different algorithms or solutions, we have to define what we're up against. What are the absolute, non-negotiable requirements for our system?
So this slide really sums up our design constraints perfectly. Let's break it down. Functionally, we need our IDs to be 64-bit signed integers. Why? Well, they're small, they're efficient for databases to index, and you can cram a ton of them into cache. Super important. But here's the real kicker. They have to be K-Sortable. Basically, that just means they're roughly ordered by time. And trust me, we're going to see why that is an absolute game changer for database performance. Then you have the non-functional stuff, and the demands here are just brutal. We need sub-millisecond latency, 5 nines of uptime, that's basically always on, and it has to scale out just by throwing more servers at the problem.
Right, so let's zoom in on that term K-Sortable. You might be thinking, why not just make them perfectly sorted by time? And that's a great question, but think about it. In a distributed system with maybe thousands of servers all generating IDs at the same time, getting perfect chronological order would mean you'd need some kind of central boss telling everyone what to do. And that's the exact bottleneck we're trying to get rid of. So K-Sortability is this brilliant compromise. It guarantees the IDs are mostly in order, which is just good enough to keep our database indexes happy and our writes super fast. It prevents the total chaos we're about to see.
Okay, next up, legacy systems. Let's look at the centralized bottleneck. This is all about why the most obvious intuitive solutions just fall over at scale.
This slide lays out the typical journey of centralized ID generation, and it's a painful one. You start on the left with the simplest thing, a database auto-increment. Sure, it's easy, but scaling it, it's a total nightmare of maintenance and tricky offsets. So you get smarter, and you move to the middle option, a dedicated ticket server. Flickr actually made this famous. It's an improvement, but now you have this huge single point of failure. If that server goes down, your whole system stops generating IDs, and it's a network bottleneck. Finally, you might try pre-generating big blocks of IDs. This is definitely faster, but now if one of your app servers crashes, poof, that whole block of thousands of IDs it was holding is just gone forever. You get these huge, wasteful gaps. You see the pattern? Each one is just a band-aid, not a real fix for that central bottleneck.
And this piece of code here, this is basically the peak evolution of that centralized idea. It's called a dual buffer ID generator, and the concept is actually pretty smart. You've got 2 buffers. You're serving IDs from one active buffer that's already in memory, and while you're doing that, a background thread is busy fetching the next block of IDs. The whole point is to hide that network lag of talking to the central server. You can see the logic right in that if block. It's checking if it needs to go get the next batch and then fires off a background thread to do it. It's a neat trick, a really clever optimization, but at the end of the day, it's still stuck. It's still completely dependent on that one central server.
All right, so if a central point is the problem, what's the obvious answer? Get rid of it. This brings us to uncoordinated IDs, or what most of us know as UUIDs. We get total freedom, but it's a compromise. And as we'll see, that freedom comes with a pretty hefty price tag in terms of performance.
And here it is, the fundamental trade-off with UUIDs. On the one hand, you get exactly what you wanted, near zero chance of collisions. I mean, with 122 bits of randomness, you're set. That's awesome for a decentralized system. But the other side of that coin is a big one, storage bloat. These things are 128 bits. That's twice the size of a 64-bit integer.
So for every billion records, you're paying double on disk space, double on RAM for your indexes. It adds up fast. Plus, the classic UUID v4 is totally random. It has no time ordering at all, which, as we'll see, is just a nightmare for databases. Now, newer versions like UUID v7 are trying to fix that ordering problem, but you're still stuck with that giant 128-bit size.
Okay, listen up, because this slide is the money shot. Honestly, every single person who works with databases needs to burn this image into their brain. On the left, you see paradise. This is what happens with sequential K-sortable IDs. Every new piece of data just gets tacked on to the end of the B-Tree index. It's beautiful. It's fast, it's efficient, your cache loves it. Now, look at the horror show on the right. That's what happens with random UUIDs. Every single insert is a new adventure, landing in some totally random spot in the index. The database has to work like crazy, doing expensive disk reads to find the right page to update. And even worse, it leads to this thing called page splits, where the database has to constantly reshuffle its index pages. And the numbers here are just insane. With sequential IDs, you might get, 10 or 20 page splits for a million records? With random UUIDs, you're looking at over 5,000. That's not just a small difference. That's a 50 to 70% drop in your write performance. It's absolutely brutal. So, okay, how do you even begin to fix that randomness problem? Well, say hello to UUID version 7. This little C++ snippet shows you the magic trick. The whole idea is to make the UUID sortable by time again. And how does it do that? It grabs the current time, a 48-bit timestamp, and shoves it right into the front, into the most significant bits of the UUID. You can see the code doing it right there with that bit shift, pushing the timestamp to the very beginning of that 128-bit value. The rest of the bits, they're still random. So what you get is an ID that a database can actually sort by time, which is a huge, huge win for performance. But it still hasn't solved our other big problem. It's still 128 bits.
And that brings us to the snowflake paradigm. This is the coordinated solution that really pulls together the best of all these ideas. It's about achieving the best of both worlds, a 64-bit K-sortable and decentralized ID. All right, let's break down the anatomy of a snowflake ID, because it's just so elegant. On the surface, it's just a 64-bit number, but how it's packed is pure genius. The first bit is just a sign bit, always kept at 0, so our number is always positive. The next 41 bits, that's the magic. It's a timestamp, measured in milliseconds. But here's a super clever trick. It's not based on the 1970 Unix epoch. You get to define a custom epoch, like the day your service launched. Just by doing that, you reclaim all those years of wasted time and stretch the ID's lifespan out to almost 70 years. After that, you've got 10 bits for unique machine ID, which lets you have 1,024 servers in your cluster. And the final 12 bits are a sequence counter. This lets each and every one of those machines generate over 4,000 IDs every single millisecond. It's decentralized, it's K-sortable, and it's all packed into one tidy, efficient 64-bit integer.
So how do you actually build this thing in code? It's all about super fast bitwise operations. It looks complicated, but it's really simple. This C++ function takes our three ingredients, the timestamp, the worker ID, and that little sequence number. First, it takes the timestamp and shifts it 22 bits to the left. Boom! That puts it right at the front of our 64-bit number. Then it takes the worker ID and shifts it 12 bits to the left, slotting it in right behind the timestamp. And finally, it uses a bitwise OR, that's that little pipe symbol, to pack the sequence number into the last 12 bits. And that's it! You have a single, perfectly formed 64-bit ID. It's elegant, it's simple, and it is insanely fast.
Now, here's something really important to understand. That 41, 10, 12-bit layout, it's not a rigid rule. It's a template, and that's one of Snowflake's biggest strengths. You can totally tweak it for what you need. Take Instagram, for example. They needed to encode a database shard ID right into their IDs, so they just rejiggered the bits to make space for a 13-bit shard ID. Or look at Sony. They needed a huge cluster and a longer lifespan, so they traded a little bit of time precision, going from milliseconds to 10 millisecond chunks, and that freed up enough bits for over 65,000 nodes and a lifespan of 174 years. There are even versions like HLC Snowflake that use hybrid logical clocks to handle clock drift better, and that's a huge real-world problem we're about to get into.
And this slide just drives that point home. Look how simple it is to implement these variations in code. The core logic, the bit shifting and the ORing, it's exactly the same. The only thing that actually changes are the numbers you're shifting by. That directly maps to how many bits you've decided to give to each part.
For the Instagram version, you shift the timestamp by 23 bits. For the Sony Flake version, you shift it by 24. We're talking about tiny, one-line changes in the code that let you completely customize the ID for your specific system needs. It's incredibly flexible.
Okay, so we've got our perfect algorithm. Awesome. But, an algorithm on a whiteboard is one thing. Getting it to run 24/7 in the chaos of a real production environment, that is a whole different ballgame. So now we move from theory to reality. Let's talk about the messy parts.
When you go to production, you're going to hit two big categories of problems: time problems and space problems. So let's look at the time problem on the left, clock drift. What happens if a server's clock gets corrected and suddenly jumps backwards in time? That's bad. You could end up reusing timestamps and generating duplicate IDs. The fix, as you see in the flowchart, is to catch it. If it's a tiny jump back, the code just waits in a little loop for a few milliseconds for time to catch up. We call that a spin wait. If it's a big jump, though, you have to fail the request. Uniqueness is king. Now, on the right, we have the space problem, worker IDs. How do you give each of your 1,000 servers a unique number from 0 to 1023? The old way was to use something like ZooKeeper to hand them out. But wait, that's a central coordinator. We're back to square one. A way more elegant and stateless solution is to just derive the ID from something that's already unique, like the server's IP address. No central point of failure. Problem solved.
So how do you actually deploy this thing so your apps can use it? Well, you could just package it as a library. But then you have a maintenance nightmare. Imagine trying to update that library across hundreds of different microservices written in different languages. No thank you. Okay, so what about a dedicated microservice? Better, but now every single time you need an ID, you have to make a network call, which adds latency. The sweet spot, the best answer is what you see here, the Sidecar pattern. You run the ID generator in its own little container, but it lives right next to your application in the same Kubernetes pod. They talk to each other over localhost, which is blazingly fast. So you get the speed of an embedded library, but the operational freedom of a separate service. It is literally the best of both worlds.
And here it is. This is where it all comes together. This is our ultimate architectural blueprint for a system that can handle a billion-scale traffic. So let's recap the key points. We're using a 64-bit Snowflake ID for that sweet, sweet B-Tree performance. We're getting our worker ID statelessly from the pod's IP address, so there's no central bottleneck. We're using NTP smearing to handle time sync and avoid clock jumps. And we're deploying the whole thing as a super fast, language-independent sidecar for crazy low latency. This is it. The whole package, ready for production.
And you know what the best part is? This isn't just theory. You can go play with this right now. There's a full, open-source C++ implementation of this entire architecture up on GitHub. Just look for the CPP tracing/node ID generation repo. It's got everything we talked about, standard Snowflake, Sony Flake, even that clock-resilient HLC version. It even comes with a test app and a simple script to spin up the whole sidecar setup in a local Kubernetes cluster on your machine. So you can literally download this and run the exact system we've designed today right on your own laptop. But wait, there's more. We're not quite out of the woods yet. Our K-Sortability was a hero. It solved that awful B-Tree fragmentation problem. But in a funny twist of fate, it actually creates a brand new, much more subtle problem in certain databases. So let's dive into these advanced topics. And this leads us to what I like to call the right hotspot paradox. It's a real head-scratcher. So in a database that's sharded by key range, our perfect, sequential, K-sortable IDs, the very thing that made our writes fast, now create a huge problem. Look at the diagram on the left. Because the IDs are always increasing, all of the new writes are hammering the exact same database shard. All the other shards are just sitting there bored. We've fixed one problem only to create a new one. So how do you fix this? The solutions are on the right. The goal is to scatter the writes. You could use a composite key, maybe sticking a user ID in front of the Snowflake ID. You could use a different sharding strategy, like hashing. Or, my personal favorite, this really cool technique called bit reversal. You literally just flip the bits of the ID around before you save it. It sounds crazy, but it perfectly distributes the sequential numbers across all your shards. Problem solved. Now, maybe you're looking at all this stuff, sidecars, clock sync, hotspots, and you're thinking, wow, that is a lot of work. I do not want to build and manage all that. And that's fair. This is where modern managed databases like Google Cloud Spanner come in. They basically say, don't worry about it. They can take this entire complex problem and just handle it for you, deep down in the database layer, completely hidden from view. And just look how simple it can be. Remember that whole right hotspot problem and that clever bit reversal trick? In Spanner, you just run this one line of SQL. You create a sequence and you give it one option. Sequence kind equals bit reversed positive. That's it. You're done. From now on, Spanner automatically generates the ID
and reverses the bits for you before it saves the row. It completely handles hotspot mitigation for you, and you never have to think about it again. It's an amazing example of a powerful abstraction that just makes a super complex problem disappear.
So, what a journey, right? We went from a simple database counter all the way to a super sophisticated, stateless, decentralized ID system that can handle planetary scale traffic. We've tackled storage, write performance, clock problems, even database hotspots. We've built a system that could outlast a human lifetime and handle 1 trillion transactions. Which leads to the one final question that every good engineer should always have in the back of their mind. What did we miss? What's the next bottleneck we haven't even anticipated yet? Because there's always one. And that right there is the perpetual challenge and the fun of engineering. Thanks so much for joining me.